So I wanted to kind of just dive into the concept of fork and exec a little bit more to kind of show you how that actually works underneath the hood. I think books in general, they don't do a good job in explaining what it is to anybody who's new, especially when um, we are actually not used to understanding how processes are created. So what I'm going to talk about today with fork and exec, and we really mean by fork, right? And
Hmm.
exec, like literally, is all towards Linux. Okay. Um, this is also applicable to Unix too, but not Windows. Okay.
Okay.
Okay. This part, I actually don't really know how it works, but there is a system call on that side called create process, and that has some sort of parameters. It's actually what you would expect, I think, where you just need to create a process in one call. But for fork, it's a two-part. Or actually, for creating a process, it's a two-parter. Each one of these serve a different role. Okay.
Yep.
All right. So how does this work in like at a like a theoretical level? Suppose you have like a task. Okay. Now in Linux, we call processes task. Okay. Say you want to actually create a new process from T1, task one. What you actually need to do is you need to actually first call fork, okay, to create actually a copy of the current process that is calling fork. In this case, T1, when it calls fork, a copy of T1 is created. Okay, so ignoring any optimizations performed by the Linux kernel, what a copy really means is everything that is related to memory management and like files and things like that. So like the stack, the register, and the virtual address space is also copied over, ignoring any optimizations. Okay. So when the fork happens, what ends up happening is that not only is a copy of this process created, but the PID of this child process is also returned back to the parent. So in this case, for example, if the parent has a PID of 1, 2, 3, when fork happens to create this new process, of course, there needs to be a PID, a process ID, or a PID assigned to this child, correct? So otherwise, they would just mean the same process, and there wouldn't be any primary identifier for the process in the system. So we would actually then assign a PID to this new task here, and we could just call this as like 241, for example. This 241 is returned back to the calling parent. Okay.
Okay.
All right.
Does that
So
always happen? Like whenever a process is created, a new process is created, it always returns back their specific PID. Like, is that like
okay.
always gonna happen?
Yeah. Okay. So let's be careful of our terminology. I think this is my fault. Okay. So fork is not. It does create a process, right? It creates a process. Creates a process. Okay. But this process is a copy of the caller. In this
Okay.
case, parent. So let's make sure that we understand that part. Okay, that's what fork is.
Okay.
So
I'll use the correct.
yeah, it's not exactly like a new process. It is a new process, but the program itself is still the copy of the parent. Okay, But to truly answer your question is, do we always get like a PID back here, right? And that answer is not always. PID can return several values. PID can return, or sorry, fork can return several values, okay? Fork returns either a -1, a 0, or some non-zero number that's positive, okay? When fork returns -1, that means fork failed, okay? And that could be a result of like lack of memory or like user permissions and so on, okay?
Mm-hmm.
So actually it's good practice to always check to see if fork succeeded, but we'll dive into that later. When fork returns 0, what that means is that we are currently in context to the child process. So the copy. So basically child. Okay? When fork
Mm-hmm.
returns greater than 0, that is PID of child, that means we are currently in context to the parent. Okay? So let's actually dive what this actually means. Like, why does this even matter? Why do we need to know the values of the result of a fork call? Well, as it turns out, let's say, let me put it this way: when you actually call fork in a process, you're taking responsibility as a process calling fork to be a parent. Okay, so when you call fork, you create a child process in this case. So you're actually responsible for the child now. And being responsible for the child can mean many things, but all you have to know is that you always get back the PID of the child, right? But the thing is that since you're creating a copy of yourself, that means a copy of your current value of your registers are also copied. Now, in this case, it also means that the instruction pointer is copied. Does this make sense? So like
Mm-hmm.
if if you had a parent right here and then you had some code, okay? And then you had, let's say something like PID T V equals fork, okay? And then you'll just say print V. I'm just using pseudocode, okay? And then you have other stuff here, okay? If your instruction pointer, and we'll just call it IP, which is a register, right, calls fork here, what ends up happening is that you also create a copy of the process, right? Meaning that
Mm-hmm.
you also create a copy of the code segment, and you also have the same copy of your code here because you're a parent process that just created a copy of itself using fork. So it's exactly the same program in this case. But again, not just your program is copied, but also your register values, which would mean the instruction pointer is also copied. Okay. So at a certain point, these values will be assigned something, right? Or for this one, the assignment actually doesn't come after until the return of the fork. Now, when the return of the fork happens, the instruction pointer is incremented here, and the instruction pointer gets down to here. Okay, by the time the child
Mm-hmm.
actually runs, now here it makes sense that the value here would be a non-zero because that's what fork returned, right? When you had created a copy and the program continues to execute on the child's side, well, what ends up happening is that really this value is not populated at all, right? Because the stack copying and the registers copying happened before this fork returned. Okay. So what really happens is that the child actually starts beginning executing its code after the fork call. So when after the fork call, this gets a default value of 0, while this gets a default value of, let's say, in this case, 241. Does this make sense?
Yeah.
Yeah. So what I mean by copying here is that if you look at the memory model, right, this is really just a zoomed in version of the code segment. Whereas you have something like constants here, and then you'll have like a heap here, and then you'll have a stack here, right? Similarly, you'll have a stack here, a heap here, you'll have was it constants, and then you'll have code, and just pretend this is a zoomed in view of that. This thing here is a zoomed in view of this segment here. So far, so good. Does this make sense so far?
Oh yeah, it makes sense. Can you hear
Yeah.
me?
Yes, I can hear you.
Okay.
Okay. So now that we know that a fork just simply creates a copy, okay? Why would you even want to do that, right? Like, why would you even want to create a copy? Like, so the first thing you should know is that this is the only way to create a new process. So a copy of itself. Okay. But you want to usually create a new process for various things. Like some things are like this. I want to execute a new program. Say you want to spawn a bin, or let's say you want to spawn, I don't know, another bash shell or work, any other work, right? Or you want to do work in the background, or you, let's say you want to distribute workload among various processes, right?
Mm-hmm.
And stitch it back together, for example. So that's what we normally want to do. But the copy doesn't really get us there. We just get a copy of the parent process. And thinking about it, that's kind of useless. Like, why would you want to create a copy of the parent process with fork and then just have two of the same thing running at the same time, doing the same exact thing? It doesn't really make sense. So usually, like I said before, when a process calls fork, it is now their onus to actually manage what to do afterwards, right? And there's like a very famous block of code that I feel that I should introduce to you now that actually shows you probably like 95% of the time we do fork in terms of the logic. Okay. It's like
Okay.
literally like 95% of the time it looks like this in C.
So
Okay.
basically, I should memorize it.
Basically, yeah. You should you need to understand it, but memorizing is easy enough.
Okay, cool.
Okay.
Thanks.
Okay. So, first of all, there's something called a PID-T type. Okay. The PID-T type is just basically type def for an integer that relates to a PID. It's just like a label to tell the compiler or like us that this number is going to be a PID. Like we should refer this number to be a PID, essentially. Okay.
What
It
you
is an
said?
integer, like underneath the hood.
So does that mean PID thread or something? What's the T mean?
PID type. Just like how we do, yeah, you know how we do size of, right?
Uh-huh.
You know what that returns? It's the number of bytes, right, that you want to allocate, correct,
Mm-hmm.
in a malloc. But that
Mm-hmm.
type is actually a size t.
Okay. Okay, got
Yeah,
it. Thanks.
yeah. These are just hints for the compiler. Uh, Technically, C has like no real types. It's just all based off of hints that you give to the compiler. So anyway, so this is the data type that actually represents a PID. So we usually will just kind of declare like a variable and assign it right away with a fork call. Once that happens, it's always recommended that you check to see if this PID is -1. If it is, it's usually best to just end your program or, do whatever you think is best now that you can't do what you need to do. So good practice is to check for that and just emit some sort of error. Right? With some sort of message, can't fork, for example. Okay. Now here comes the interesting part. Remember, if you're forking, it means that you have to take care in actually understanding whether or not you're still in context to the parent or you're going into the context of the child now. Because why? When you fork, what ends up happening is that the child begins executing the same code because it's a copy, right? And it'll be right here. So at some point, if you want the child to be doing something different, you actually have to check to see if the PID is actually 0. If the PID is 0, it means that actually this is going to be the child. If it's not 0, that's the parent. So it's as simple as this if condition here. If child PID is equals to 0, then that means we can just print something like this. Print F, this is the child. And we could do whatever we need to do here to accommodate that. Otherwise, we'll be at the parent. This is the parent. Because that's the positive 0 case in this case. And we could do whatever we want as a parent.
Mm-hmm.
So this is actually the normal flow. Okay?
Okay.
Because again, they're a copy of the program.
Mm-hmm.
So the child's going to execute the same code. So therefore, we always have to check to see if the child is a child or if it's going to be the parents continuing on from this fork call up here.
Mm-hmm.
Okay. Now, this
Yep.
isn't exactly like the complete thing. What's actually missing is that there are certain caveats to this. So the first caveat is that when we create a new task, for example, so we have T1 and then we create a new process in the tree, right? And this is also T1. So this is 2, 4, 1. This one is 2 or 1, 2, 3. Make sense? This in turn could be
Mm-hmm.
a child for some other process, and this could be like T2 and so on.
Yep.
Okay. And this is a process
Mm-hmm.
tree, right? This could just be init, for example. Doesn't really matter. Okay. There's an important thing here. If your code, let's say the one that forked the child, so being the parent, so we're looking at T1 here. If it actually dies,
Mm-hmm.
meaning exits or errors out before the child completes, you're actually left with an
Yeah.
orphaned child. Okay.
Okay.
So that
Yep.
means that the child is going to hang. Okay.
So what happens when a child hangs?
Many things. It could actually not complete correctly, or it just won't run
Mm-hmm.
normally.
Okay.
Yeah. So what you need to do, there's so many tricks to this. You could like do this double fork thing. You can also reattach this child to another parent. You could do other things, but the simplest way to ensure that your child completes after or before your parent completes is to have your parent wait for the child to finish using
So have the parent wait for the child to finish.
uh-huh.
Wait for the child to finish. Okay.
Okay. So
Sorry.
here's the
Mm-hmm.
flow. Yeah. No, it's fine. Because if the parent finishes before the child, then the child's gonna hang. So what the parent has to do is wait for a signal. Okay, and this is one of those sig blah blah blah, like
Mm-hmm.
those sig pills used, whatever those things, right?
Like
So
one of those signal calls
yeah,
or
yeah,
is
yeah,
that what-
yeah. Yep.
Mhm.
Yeah. So the API call for the parent to use is, let me make it a different color. Come on. Use my mouse. Okay. It's called wait id. And that takes in the PID of the child. Oh my gosh. Okay. Child PID,
Mhm.
the status, and options. I just usually just put 0 whenever I do this. Okay. So the child PID, you know what that is. It's basically this one up here.
Yep.
Okay.
Mhm.
The status variable is actually another variable you have to declare and maintain. Okay. This status
Mhm.
variable, you pass in actually the pointer to it. So the pointer to this integer, so you can turn this into a pointer by using the ampersand right here. Okay.
Okay.
What this
Mhm.
status is going to contain is the return code of your child. So if your child exits with code 0, this will contain that exit status or exit status relating to it. And this
Mhm.
is how a parent can understand what happened to the child. Okay, so this wait PID, think of it as like a infinite loop until the child is done, and then that loop breaks, and then the parent can do whatever it wants after that. Maybe like exit, for example.
Okay.
Yeah, and you may have heard the term like zombie process or things like that.
Yeah.
Yeah, so when a child process exits, it's not actually exiting right away, right? There's some traces of it are left, and you might have seen this in like your system monitor or like B top, A top, H top, whatever top. When you exit
Mhm.
like a program, you kind of see like hanging around just for a little bit.
Yeah, I do.
Yeah.
Mhm.
That is because basically the OS has cleaned everything up already, but it's leaving a shell of it alive. I think it's just the data structures, simply because it needs to be kept around for this variable right here. It needs to communicate. It's just waiting for the communication back to the parent to acknowledge that the status was received. When that
Okay.
status
Yeah,
is
I
finally
understand.
emitted through back to the flow, yeah, the child can actually just be removed from that system monitor or whatever you call it. It'll be completely exit after that, no longer a zombie.
So is it more for accounting reasons?
Well, I mean, it's also just for that, just to make sure that the parent eventually receives the status. Because if the child exits too quickly and the parent isn't scheduled to run,
Mm-hmm.
it won't get the status.
Okay,
Because
I see.
it's because the child has that status, right?
Yeah.
Yeah. So and remember, we had to think of them as executing in the queue. You know, ready, running, stopped, blocked, whatever states in the scheduler. So the parent isn't
Mm-hmm.
necessarily like executing when the child exits, right? It could be back in the queue somewhere.
Okay, I see. Mm-hmm.
Yeah, yeah, yeah. So it's actually internally I said it's like a infinite while loop, but think of it as also like sleeping. The parent will just sleep.
Okay.
Yeah. Okay. So yeah, enough of this, right? This is too theoretical. Let's actually dive into some code just to demonstrate what's going on here.
Sounds
Okay.
good.
So I'm going to show you two examples, or I'm going to show you a few examples. One is just the normal flow that I just have written in our Excalibur right now, just so that you can see that in action. So I'm just gonna make a new project and I'll call it fork example one. And then I'll just create a new file, main.oops, touch main.c. Where is it? Touch main.c. Okay, that should be here. Oops. It should be here. Oh, I
I
created
think.
it up here. Ah,
Yeah.
okay, okay, okay. So as always, I start my programs pretty much the same way each time. I like to include these headers, but the most important one that will contain the fork and exec is going to be the unistd.h. Okay.
Mm-hmm.
Unistd.h, if we actually just control click into it, oh, it doesn't work. Let's see, man unistd.h works. You know what I'm gonna do? I'm gonna do pacman SYU. Let's do man pages.
So that installs the man pages for the kernel, or
Yeah, but I'm
what?
also
What does that?
I accident so it's gonna install man pages in general, but I'm also doing a system update at the same time.
Okay,
Yeah,
cool. So
yeah. I'm
since
not.
I'm on Ubuntu,
It's a different package. Yeah,
okay,
I could link with you on that one later. Uh,
okay, thanks.
yeah, yeah. I shouldn't have done the SYE. I don't know why. I thought I updated and everything already. So I thought it would be small.
Now we know.
Okay, okay. Did I get man pages? Man to fourth. Okay, I did. Okay, so now I have the man pages for system calls, right?
Mm-hmm.
So this exists in the standard C standard library. I wonder if it tells us here. Yeah, there we go. So it tells us that it's actually included with unistd.h. So that's where you can get your fork call from. Okay.
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 Yep.
So let's do something here. Let's actually just declare this and just get on with it with pid t child pid equals fork. Okay. And I can say something like if child pid is one, never negative one, I want to print
Mm-hmm.
out an error and just say Sorry, I hear like an echo, like now it's like getting thrown off.
Yeah. Uh-huh.
Sorry, okay. I don't hear myself. Wait, are are I think your microphone is picking up my own voice.
No, I'm on a headset though.
Oh, it's weird. Okay,
I haven't
I'll just
changed
deal with it.
anything.
Yeah,
Okay.
yeah.
Here.
I'll just deal with it. Yeah. Hello. Can you hear me?
Yeah, is that better?
Oh, that's way better.
Okay, yeah. It was on the whole time. That
Oh, okay. Well, this is better. Okay, I can hear myself now. Okay, or at least I can hear my brain now. Okay, so if the child paid is -1, we just want to print out an error. Okay, so std error. So output this logging to the std error pipe, and then we can just say could not fork. And I really don't care what the reason why. We'll just exit 1. Okay. Otherwise, if child paid is 0, okay, we know that this is going to be the child. So we can print F, we can print out the child PID, and then we can say this is the child. And then we'll just pass in that child PID as a variable. And then after that, we can say printf here, child PID is ND. This is the parent, child PID. Okay, exit there. Okay, so we want to return, oops, we want to return 0. Okay.
Yep.
So that's a quick demo, and let's just see what happens. So if I go into the fork example 1, I'll do gcc main.c, and I'll execute it on that. Okay, so notice how like the parent executes first and then the child, right? By luck,
Yep.
this is working out pretty good. Like you see that the child PID is non-zero, and this is the parent in this case, right? The child PID here is gonna be like 10008, whatever. But then on the child side, when that fork happens, remember the instruction pointer is kind of relatively at the same spot, right? Except that it's going to check that it's going to be 0. So then it's going to output this is a child in this case, because this is the exact same program. Okay. Now, to prove that it's the exact same program, what if I did int x equals 3? Okay. Or better yet, what if I did something like int argc character argv, okay? And I just said argv, or x is going to be argv1, for example, okay? If I were to output x here, okay, what would I get for both parent and child? Do you think you could take a guess?
So since argv1 is assigned to x, I guess the child PID would be x.
No.
Yeah.
The child PID is already assigned, right?
Uh-huh.
But what is x in the child?
Oh, x in the child is 0.
Okay, let's see. Oh, a to I. Okay, so a dot out, but then we need to pass in an argument. Let's do 789. So if I did that, the parent gets 789. That makes sense because that's the original program, right?
Uh-huh. Oh, okay. So 10057 is the PID of the parent.
The child. See, this is confusing, isn't it?
Yeah.
Yeah. So when the child PID is non-zero, that means that is the parent. The execution here is the parent's execution. When the child PID is 0, that means this is the child that's executing.
Okay. Mm.
Does this make sense?
Yeah.
These are outputs from 2 different programs actually that just ran at the same time. These are 2 different programs that just ran at the same time. That's why you see 2 outputs consecutively. They both ran at the same time. It's just that one is the original program that you ran, which is this one.
Mm-hmm.
And the other one is actually the child that you just forked.
Okay.
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 So my question here was the main program, right? I ran the main program, the parent here, with 7, 8, 9 as the argument to the program. Okay.
Yeah.
It makes sense. This one is the parent. Let's focus on the parent here. Okay. Let's focus on the parent. On the parent side, I outputted X, right? I outputted X and the child PID. So far, so good?
Yeah.
Okay, so where does X come from? X comes from here, which is argv1, which is argv1 here too. So far, so good?
Yep.
Okay, child PID, that's easy. Child PID is coming from the result of that fork call.
Okay.
Okay, so it makes sense we get 7, 8, 9 here because that's from here, right? We also get 10, 0, 5, 7 because that's a result of fork. Therefore, when we print out X child PID, this is the parent, then that's the result we should expect.
I see.
Okay? But what about when we had forked on the other side, the child? The child was 0, child PID was 0. That makes sense, right?
Yep.
That makes sense, doesn't it?
Yeah.
Yeah, but how the heck did X come? We printed out X here on the child process. How did that come about? How is that 7, 8, 9?
Was the process for the child created and then it ran the next line? Is that how it works? I actually don't know.
Well, if okay, let's think about it, right? And this is the reason why I said there's a lot of details to juggle. There's a lot of rules that you have to remember. Okay, what's the key thing when I said when you fork a process? What is a main key thing? When you fork a process, it is essentially a what?
A copy of the parent process.
Meaning that you get a copy of
the stack,
the heap, constants,
constant,
and
the
code.
Uh-huh.
Okay. So if I executed this, isn't X just the same X from the parent? Because I declared it on the parent stack here. The child receives a copy of the stack, doesn't it?
Yeah, it does.
So therefore, it does have a reference to the X variable too, because it's the same copy. It's a copy of X.
Yep.
Remember when you had forked, the child starts executing here, right? X was already declared at some point.
Oh, I see.
So when you had created a copy of the parent, yes, go on.
Are you seeing that since X was declared within the parent, and when the child process is created, it gets exact copy of the parent. So that's why we see X as 7, 8, 9. Okay.
Yeah.
I see.
That's a key detail, right? Like I said everything, like the memory, like the stack, the registers, those things are copied. So therefore you get X as a copy too, because it happened before you assigned X before you had forked. Therefore, it was part of the parent state in this case.
Okay, I get it now.
Okay. Now, so that's a good example in showing that there's this copying thing going on, right? Now the next thing I want to actually show here is, well, we've been getting lucky where the child is not really hanging, but technically the child, it does end up hanging if I didn't wait for the child to finish as a parent, right? So remember I said that you need to have a status variable too?
Yeah, you did.
Yeah. So let's say we didn't do that and we decided to fork and just for whatever reason, this is a child, right? The child does some sort of expensive work. Okay, let's just have a function for it to do some expensive work. Okay. Uh, so we'll say void expensive work void, and we'll just do something stupid to pretend it's expensive. We'll just have it sleep for 5 seconds. Okay, and that's
Mm-hmm.
coming from what library? Let's see what library is this coming from. Man 3 sleep. This one's coming from UniSTD. Okay, so good. And that takes in seconds. Okay, so I'm saying sleep for 5 seconds. Okay.
Mm-hmm. Mm-hmm.
All right. So let's have the child do some expensive work. Sleep, or sorry, expensive work. Okay, a function call that calls for expensive work. Now, you can tell whenever our process exits, right? Like we get a new prompt after we run it, right? So in this case, when I do a.out, uh, when I do a.out, I get a seg fault. Why? Why am I getting a seg fault? That's weird. Oh, duh. I didn't pass in anything. There we go.
Cool.
Okay. Yeah. I'm supposed to pass in something. You know what? I'm gonna stop myself from being stupid. If argc is less than 2, f print f usage a.out number exit 1. There. I'll stop myself from being dumb again. All right. So let's do that again. Oh, that's the error. Okay. Here a.out. Okay, that protects us now. Okay, we're protected. Okay, 789. Okay. So expensive work. We're supposed to be sleeping. I have no idea why that's not sleeping. Int y equals a is going to be y times 2, and then we'll just print out this case. Let me do this and I'll explain. Okay. Great. That is sort of what I want. And then I didn't print. Why is that? Okay, yeah, that makes sense actually. Okay. So I have this expensive work function, right? And it's just simple as like sleeping for 5 seconds, and then it'll just multiply some number by 2, and then returns that number as a result. And I just try to catch it here, right? So I want to pass in 4, therefore I expect 8. Now, if I run this, I don't get down to this call at all, right? I'll make it even more clear. Notice something peculiar here?
It
Did you
doesn't
see
hit
that just
the
happen?
hello. Oh, it took a long time for it to
Uh-huh,
show
uh-huh,
hello. What
uh-huh,
happened?
uh-huh. And it showed 8, right? That's 4
Is that
times 2
the
is 8.
result of the child process?
Yes, 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 yes. Let's do
Oh,
something more
okay.
obnoxious. Let's do something more obnoxious. Okay. So let me just do this. Okay. Do it again. Oops. Let me compile. But this is probably gonna be this. Watch. It's just gonna come. Yep. You see that?
Yeah.
And that completely breaks my shell. That really does break me. So if I did this, I should be seeing 246
Mm-hmm.
in 5 seconds. But now I can't do anything. Look at that. I can't even like do stuff properly. I'm in a weird state. So that's actually not how you're supposed to do it, right? Because the thing is that the parent is actually exiting before the child completes. And that's leaving the child to be an orphan process.
Oh,
So how do we fix
okay.
that? So remember, it makes sense now, right?
Mm,
Remember I told you we need this and we need to call this wait PID. And
mhm.
that will usually go here.
So are you saying that
Okay.
the status should be some sort of response from the child back to the parent?
Uh-huh. hmm Makes sense.
Yep.
So let's do it. Let's fix our program. Let's have our parents sleep until the child is done, and then like do the have things just exit correctly. So let's clean
Mm-hmm.
that up. So let's declare a variable called status, right? In status. And then what we're going to do is we're just going to do wait PID here with the child PID. We're going to wait for this child PID and put the status at this address and no options. Okay.
Mm-hmm.
And then we can just print F real quick. Child has exited. Just to let us know. So far, so good.
Yep.
So given this status, this is going to store the status. Actually, just do this with status. How's that?
That sounds good.
Yeah. So this wait PID here is going to put the parent process to sleep until the child is done.
Mm-hmm.
So if we were to compile it, implicit, did we need, oh, yeah, sorry, I need to tell you something. Wait PID needs another header included. It's called syswait.h. Okay. You need this
Okay.
to run this. Yeah. So I did that again and I ran a.out one, for example. Notice how it's just waiting now. And there you go. Child has exited with status 0.
Mm-hmm.
Right? Let me make a new line here so that's easier to see. So okay, 1, 2, 3, 4, 5. Child has exited with status 0.
Cool.
Okay, so what happens if I have the
Mhm.
child then exit with I don't know, the 23? Okay, let's compile that again. Let's see, 1, 2, 3, 4, 5. Okay, 5, 8, 8, 8. No idea what that is.
Mm-hmm.
So these status codes are actually
Wait,
bytes. Byte.
5888, is that because in
uh,
line number 22 in status we did not assign it a 0 or something?
Yeah, yeah. So you get some
Like
you get some sort of
random
garbage
number?
because
Yeah.
yeah, you get garbage because of the bits, right? Like the exit codes are 1 byte. They go from like 0 to 255 or something like that, right? So what ends up
Mm-hmm.
happening is that it fills the last 8 bits. It fills the last 8 bits, but then there's other chunk up to those other 32 bits that we have. And that's
Yep.
actually causing this to show up, right? So
Mm-hmm.
There is a library call for this it's called exit status or something like that. But basically, your train of thought is correct. Like the exit codes are usually just 8 bits or whatever. And then this helper exit status will help. Let me just do it. Things like this. Man, let's do it. Oops. Yeah. So this is a helper that will kind of like chop off like everything that is after the exit code to cleanly like to present it cleaner. But yes,
Okay.
your train of thought is correct. Like you're just seeing garbage from the 5888, but if you were to only take the last 8 bits of that 588, whatever I don't know, whatever it is, you'll see actually that it is like 23 or whatever it is in this case.
Okay, sounds good.
Yeah. Okay. So this is not a very interesting example, right? Like, well, it is interesting in that now you kind of see various things. You know that this is always copied from the parent process, and you know that you should probably wait for the child to finish.
Mm-hmm.
Like these are the things that we're learning right now, right?
Yeah.
Okay, so that's still not entirely useful. What usually we fork, and I say the 95% of the time, like the usual thing that we do is that we will almost always want to call fork because we want to create a new process. Okay. And this is essentially what your shell here does, right? It's just a big forker. It's just one big loop of forking, execing all the time. Because when I run something like echo hello, that's running the echo program. It just forked. Bash just forked itself and it
Mm-hmm.
replaced itself with echo.
Mm-hmm.
Now that replacement is actually called execing. So if I were to draw this diagram here, so now it's clear, right? I'm not going to say task one anymore. I'm going to say something like bash. Okay. So when bash calls fork, what ends up happening is that a clone of bash happens, right? So you have two bashes. And this bash returns back some number, let's say 91. Okay, that's PID. This PID is, this case, this PID could be 52. What actually you want to do is immediately after you fork, you want to call exec or some exec like thing to replace the memory with something new. In this case, it could be like echo, it could be vim, it could be whatever. It could be whatever they specify. They being the programmer or the user in this case. Yeah. So this is actually the more useful part. Like the whole forking to create a copy just to get the PID is you're gonna have two bashes. What are you gonna do with that, right? So what you want to do is you want to just you're basically forking to create like some sort of shell, some sort of entity that you can actually use to replace what you really want to have, which is which is a new program on top of this here. Okay, so actually this gets replaced. All this here gets
Mm-hmm.
replaced by this, right?
Yeah.
Okay. Now I'm gonna show you that example right now. So there's a lot of system calls for specifically this exec thing, right? There's like a exec L, there's an exec V, there's an exec PV, P, whatever. They all basically do the same thing. It's just that their arguments are different for convenience. So if I do man exec, right? I actually, okay, well, that's exec. That's not the one I want. Man to exec. Man 3. There we go. So man 3 exec, okay? So there are actually 1, 2, 3, 4, 5, 6 variations of exec you can do. All of them have basically different set of arguments you can pass in. They all serve like different purposes in terms of, or not. They all exist for the same end goal in that you want to use this new area in memory that you have copied the process, right, to, and replace it with a new program, so like a new set of everything. So something like, for example, exec L is very convenient in that you just need to pass in the file name, basically the path to the program you want to replace your copy process with. In this case, if I wanted to replace the process with Vim, I would be like bit/bin/vim, right? And then the second argument here is basically an array, or not an array, like variadic list, right, of all the arguments you want to pass in. So you know how like in every command line program, you have like a set of like switches and arguments you pass into whenever you run it. Those are the arguments, right? That's the argv that you usually have in whenever you write a C program. Those are what be contained inside argv. Okay. Now, in order to tell like this exec L, for example, that you're done passing in arguments, you have to signal it with a null at the very end. Okay, so that's like a basic use of like something like exec L. And there are like other variations too. Like for example, let's say you didn't want to just give a variadic list, right? Let's say you wanted to give it just like an array of arguments, and that will be right here. It's this one right here. This exec v. It's the same thing as this one, except that now you're putting all the arguments inside an array of strings. Okay. Oops, sorry. Okay. And then there's other variations too, like exec LE is this basically exec L, where you pass in not only with your arguments ending with a null, but also with a list of environment variables. You know those things as you export before you actually run your program, like export those variables in your command line?
Yep.
Yeah. So variations, but today let's just concentrate on exec L. These are all just things that you will just come to learn how to use eventually. So if we take this here and we'll just make their fork. Oh, we did already. Did we? Did we do a fork example 2 already? Yeah, no, we didn't. Okay, fork example 2. Okay. I will just touch main dot touch main dot C, and then we can just quickly write a simple program that executes Vim, for example. Okay. So we can do include stdio.h, include stdlib.h, include unistd.h. And I'm going to pause on actually including syswait.h. I just want to show you something. So if I did int main, right, void, because I don't want to take any arguments, and I'll just like return 0 just here. And I just simply just do that same flow, right? I would do pid-t, right? Child pid, good, fork. We're just going to fork right away. And then we're going to check if child pid is -1, then we do fprintf. That's the error. Can't fork. And then we just exit 1. Okay. Otherwise, if child pid is 0, okay, what we can do here is we can call exec L with the path to Vim. Okay, let's just do which Vim, just know. Okay, user bin Vim, user bin Vim. Okay, as a first argument, that's the file we want to execute. Okay, and then the list of arguments ending with null. Okay, in this case, there's a caveat to this. you have to repeat the program name again as an argument. That's the reason why whenever we do like the argv thing, we always start at 1 because 0 is actually the name of the program. So I don't know why it's like that, but just keep it the way it is. Yeah. Okay. And let's actually let's have it make a new file called hello.txt in this case. So we're going to execute vim with hello.txt. It's going to create a new file in this case. Okay. And exec actually returns a value. This value here, if it's actually any value, okay, that means a big problem happens. Because the thing is that you're technically, if you're replacing your child process with a new program, you shouldn't actually make it through past this exec L line at all, right? Because your program just stops at this line, replaces everything, and now you lose this program. The child is no longer running this program anymore at that point. It's running Vim now, right?
Yeah.
So the only time where this could happen, okay, so the int exec result, is if you ran out of memory to exec, or you couldn't find the file, or whatever, okay? So you still need to check to see if something is wrong, but just know that if you actually end up on the line after exec, something really bad happens. So we can just say if exec result is not equal to 0, for example, we can print f std error could not exec. And then we can just exit right away. Okay. Otherwise, we're at the parent process. Okay. What we want to do, ignoring the wait stuff so far, ignoring the wait stuff, was just print f. I am the parent. The parent's really boring. It doesn't do anything. Just I am the parent. That's it. Okay. So this is the simple like structure again, right? So we fork, we check if it's -1, the PID. If it's -1, then we can't fork. Otherwise, we check to see if whether or not the program is running as a child. If the program is running as a child, then what we want to do is we want to call exec right away with vim as the program, and then give the arguments here. So we're going to create a new file called hello.txt if we were to save it. And otherwise, if we make it pass on this next line right here, that means exec failed, because the child shouldn't be running the program still. If exec was successful, it would have gotten replaced with vim in this case. Otherwise, if child PID is a non-zero in this case, non-zero being a positive number, we're just the parent in this case. So far, so good?
Yep.
Okay, so let's actually say that. And then let's see what happens. So we do gcc main.c, clear, and let's run. Okay, so I go into Vim right away, right? I go into Vim right away because I forked right away. I forked right away. So I go into Vim right away. But, I tried to type something in Vim. I got an error. Error reading input exiting. Okay? The reason why this happens is because I orphaned Vim. Because as the parent exited, I did not wait for the child to finish. The parent literally exited after that fork call. If you see it here, right, after the fork, right, after the fork, the parent continues to run, falling into this else, and then returning 0.
I got it.
And then the exec got replaced by Vim, but then by the time that happened, the parent is gone. So that's the effect. Like you don't want to be in this state. That's not a good state to be in. So we had to fix this program by including syswait.h. Okay? And then here we have to declare a status. And it's as simple as now just waiting for the PID.
Wait, right? For the status, do we need it to be assign it something?
It's not a big deal unless you really want to check for the status later.
Oh, okay.
Yeah, it's a. You can also use the whole Wexit status helper like this.
Okay, sounds
You can
good.
use that thing. Yeah, so I'm gonna wait for this child PID to finish, pass in the pointer to status, give it no options, and this will actually wait until Vim is done. Okay, so we try that again to fix it. Okay, notice how we go to Vim right away again. Same thing as always. But now we can type. We can use them as normal. Okay? And the only way for them to exit is if we quit them. And quitting them is :Q. And when that happens, the parent ends up exiting cleanly. Everything just is clean in this state. Okay? So that's like your normal exec pattern. This is how you actually fork exec, right? You can actually create your own shell this way. Just have like a while with the accepts input here, right? Like for example, there is a helper called exec v that actually doesn't need the full path to the file. It will just listen for whatever path the current parent process is on. It inherits the environment variables. And if your path variable contains user bin, right, then bin will be able to be picked up by the OS, or sorry, your process by exec, right? So let's just say here, like I want to control what kind of process I want to run. So I could do int argc, character star argv. So too many arguments. Let's check out man exec. Not this exec, man 3 exec. Okay, exec v is, oh, it's an array of arguments. Sorry. So we just do argv. We just straight up do argv. Why? Is it exec v? Hold on. Exec v path name character constant arg v. That looks right. Exec vp. Is it exec vp? I think it's exec vp. See. Yeah, it's exec vp. So I could literally specify it to run anything I want in this space. See?
Cool.
Right. So this is minor. It's very minor. It's like you just read the documentation and learn how to use these things. But notice how I didn't need to do the full path here because exec VP will search for your path environment variables for you in this case.
Okay.
Yeah. Okay. So that's one thing. Now the last one I want to show you is what happens if we want to spawn a lot of processes to do work, right? Let's fork and exec a lot of different not threads, but like processes and have them be distributed to do something. So let's say I have a very inefficient algorithm that will sum up all numbers from like 1 to 16. No, actually, no, let's keep it simple. From 0 to 9 inclusive, for example. Okay. And that is not only that I want to sum up the numbers from 0 to 9, but I want to sum it up. I want to take one of those numbers and multiply it by like 113 and sum that. So like it'll be 0 times 113 plus 1 times 113 plus 2 times 113 all the way up to 9 times 113. And pretend that takes forever. That takes like 5 seconds to do. Okay. 5 seconds for each number. Okay. So just pretend it's like a huge expensive job. And if we just had one program to do this, how long would that take, right? It's going to take a long time. So let me just show you like how we would do that normally. So if I did fork example 3. Oh, touch me nothing. Okay. I did it again, didn't I? I should CD to fork example 3 right away. There we go. All right. So let's just do actually, you know what? Let's touch default.c. Okay, let's work with this one. Okay. So let's just do it the normal way. Like, okay, so include stdio.h, include cplib.h, include I think that's all. Oh yeah, you need std because we need something. So let's have something called like for example, int expensive function. So expensive fn we'll give it a number, right? And then we'll just return v times 13. And so this will just multiply a current number by 113. But let's just explain. Let's just pretend that it's so bad. It's like so poorly written that it takes 5 seconds to finish this function. Okay, in the pretend world. So if I had this here, and I just wanted to sum up the numbers. So let's just define a basic, sum variable. And we did for int I equals 0, I is less than or equal to, or less than 10, okay? Then I plus plus, and then we can do expensive function with I, okay? And then we want to add that, the sum plus equals expensive function, and then we're going to print f result sum, okay? Maybe 5 is too much. Let's do 3. All right. So we did GCC before.c. Okay, so now it's working. It's like crunching numbers, right? It's like really crunching. So it's like taking a while. It's taking time. It's taking time. It's taking time. It's taking time. Taking time. It's taking time. Taking time. All right, so it finished with 5085. Okay.
Okay. Uh-huh.
Did that take a long time, or was it just me?
Yeah, it took a long time. So I was wondering, what does the 3 stand for? Is it the
That's three
seconds?
seconds. Yeah, that's 3 seconds.
So
This is
with that,
fake. We're just pretending that it's super expensive. It takes 3 seconds to do this.
okay.
We're just pretending. We're just pretending. This, like, to multiply a number by 113 is just very expensive in our pretend world, just for our understanding. Okay.
Okay. Mm-hmm.
It's in our fantasy world. Multiplying a number by 113 takes 3 seconds to do.
Okay, got it.
Yeah, it's so heavy. It's so, like, you don't care how this is written. It's just, you just know that this is expensive. Okay. And just to kind of, make sure that we know things are working, it's like computing at the I. Okay. So then we have like a signal to tell us, right? So if we did this, so computing at 0, we'll be computing at 1, and then computing at 2, right? One at a time. We're trying to sum up the first 10 numbers like this, right? And it's
Mm-hmm.
very
Mm-hmm.
painful. It's very slow. Well, how can we actually solve this problem? Okay. So what if we had a parent process, okay, that actually spawned 1, 2, 3, dot, 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 uh, 10 processes to compute 0 times 113, 1 times 113, 2 times 113, all the way to 9 times 113, and have it all then send it to some sort of sync. In this case, each individual files with numbers. And then after that, have the parent read the sum of all these, or have each individual value and sum all of them up. So we can fork and exec 10 different processes to each handle their own number.
So are you trying to say like we should have the work to be distributed and then combine it all back together?
Yep. We call this
Okay.
map reduce. Map reduce. Okay. It's called a map reduce. And there's a famous paper from Google. Oh my gosh. Yeah, let's do it. Okay. So there's a paper written, maybe, I don't know how long ago, 16 years ago by now. Oh no, about 20 years ago. Okay, that from Jeffrey Dean about this type of architecture. Okay, where you spawn a bunch of workers and have it actually all feed back into a master node or a main node, right? This is just the process version of that, right? This is a process version of, of MapReduce. So we spawn basically 10 processes, okay? With fork exec to do expensive work, okay? So how will we do that? So let's do that again. This time I'm just gonna kind of build off of this, okay? And you're gonna notice a difference. So this is gonna be a little bit more programming, but that's okay. So let's include sys28.8, okay? And we'll keep this expensive function here. What we wanna do is let's create an array of child PIDs, okay? So we can do PID T, children PIDs, okay? And we want to create not 8, 10 of them. Okay, so we're creating 10 processes. Let's also create an array of 10 statuses. So far, so good.
Yep.
Now, what we want to do is we're going to fork 10 times. So we're going to do children PID. We're going to set the PID ID because we need that to wait, right? We want to wait on the individual PIDs. So we're going to do this. We're just going to simply fork. Okay. Now, when you fork, what ends up happening is that, well, the child is going to end up here. It needs to know whether or not it's a child, right? So you're going to quickly have an if statement here, if children PID. And again, since it got forked right at that specific moment, I will actually be the value of when it was forked. Does that make sense?
Yeah,
I
that makes
will be
sense.
at the right one. Yeah. So if it's equals 0, I mean, even after forking, if it still ends up being 0, right? And in xi, what we want to do is that we know what a child, okay? So, and we know what I is, right? So let's multiply that by 113 and get out of there, okay? But we want it to write to a file. So I'm going to have a helper that will build me a file name, okay? Let's do a file name. Let's make file. That will give us, that will start with an int, like basically what is the index of the file, and then we want to take in a buffer. Okay. Now, let's just quickly make a thing that builds a string. Okay, so I'll have something called char star prefix, and I'll just say work like this, and then I'll have a char that says ID. Okay, that will basically be, this is a hack, 0 plus I, for example. Okay, and then oops, sorry, and then I'll have something called char suffix. I'll just dot text here, and I'll build the file name. So I'll use sprintf, just put it into the buffer, format it the way I want. So it's gonna be a string, character, string, okay. And then we're gonna pass in the prefix, the ID, and the suffix to be replaced, and buffer should have what we want by then. It's gonna print all that into a buffer. And we'll return the pointer to the buffer.
Okay.
All right. So let's quickly make a file. Okay. So we can do a file. fp equals fopen, and then we're gonna say get make file name. And then we need a buffer, right? So let's declare a quick buffer of 15 characters. Okay. Don't think we need more than 15. So we'll pass in I, right? And the buffer. And then we're gonna open it up for writing. So far, so good?
Yep.
Okay, so we're gonna basically get int result is gonna be the expensive function with I passed in. That's gonna take it's that 3-second function, right? Okay, so once we get that result, we're gonna write to the file fp. I think f takes it. Let's see. Man f f. It takes in the format. Oh no, sorry. It takes in the file stream, the format, and the values. Okay, so it takes in this and then the format. So I'm just gonna write a simple integer, and it'll be the result, the expensive result, the result of this expensive calculation, right? And I'm just gonna f close, fp. So this is like the chunk of the work that it's gonna do. Okay. And just for the sake of consistency, I'll say processing. Like that. Okay, so we'll F close, and then we're going to exit right away. We'll exit with 0. The child will exit after it's done this. That's its only job. Its only job is to, at this current child PID, just create a buffer of 15 characters, write the compute the expensive result, write that result to a file, and close it.
Okay, sounds good.
And this file is going to be called work dash whatever dot text. So far, so good. So it does that 10 times, right? But what happens if you're the parent, right? Well, for the parent, it's easy because all children that get forked will always exit technically. Maybe we should do something like this. If children PID, let me just try to make sure I practice my own, Okay, we can't fork, then it'll just exit. But basically what I'm trying to say is that all children should never be out of this loop. Because if they do their computation correctly, they'll exit.
Okay.
Yeah. So what we want to do now afterwards, as a parent, right? So the parent's just going to keep forking, and since the children PID is always going to be a non-zero, it's going to just fork. But after that, you want it to wait for all the children to finish. So I can do int I equals 0, I is less than 10, I plus plus, and I could just call wait PID at each individual child for their corresponding statuses and 0. Okay. And you can take a pointer to that. Maybe it is. Oh, it is a pointer already. Sorry. Okay. Okay. So after that, after all, all right. Anyway, so each parent's gonna wait for every child to finish, right? So by the time all children are finished down here, this piece of code, we're going to have a bunch of text files that we would like to read out. Okay. So all we have to do again is just iterate through every single text file, get the contents of that, and do like an A to I to transform that string into a number and just add it up. Okay. So we can just do int sum is 0, and then we can just do for int I equals 0, I is less than 10, I plus plus. We can just basically then now we can trust that all the files have already been written to. In this case, I don't need this part, but I would like results to be fgetS buffer. In this case, or not reuse a buffer. Sorry, let me just back up. Okay. So we want to iterate through 10 times now to get each individual file, right? So we're building up the file name again, but now we're not going to open up for writing. We're going to open this one up for reading. Okay. So what we want is we actually want to store the data inside the file as an integer, right? So we first need a buffer for that. So it'll be a char data buffer, and it's gonna be 80. Let's just say we'll read the first 80 characters of that line, and then we can say f get s in this case, and I can't remember what that looked like. F get s is gonna be the buffer we want to read into, the size of the data, and then the file pointer. So we want to read into data buffer, the size will be 80, and then the file pointer. Okay, so at this point, data buffer has something. So we can just do sum plus equals a to I data buffer. Okay, so we're going to come thing, and then we're going to close it, and we're going to keep doing that for all of the files that we have here. Okay. So let's actually see how fast our program is now. So basically, we're just kind of multi-processing now. Okay, we're making use of our CPU. So yeah, let's have at it. So to demonstrate this, I am also going to execute btop. I have btop. Okay, let's just do btop. To demonstrate this, I will use btop. Okay, I'm going to filter a dot out. I don't know if that's going to show anything, but GCC main.c, ooh, lots of stuff. Passing one argument to f open makes pointer to the start from the very beginning. Okay. What's going on here? Oh, other way around. Okay. Okay. Children PID at what? I. Okay. And now what? Statuses. Oh, it is. Sorry, my brain failed me on that one. Okay. Redefinition of sum because I did sum up here. Okay. Okay, we're clean. All right. So let's check it out. So we processed everything. See, and you see BTOP coming out with all threads, and we're done.
Mm-hmm.
Did you see that? How much faster?
Can you run it again? I want to see if it shows up in. Oh, okay. Oh, I see all of it. All the processes.
Yep.
The child
Yep.
processes. Cool.
Yep. And we got 5085 as usual, and we went so much faster. We went 10 times faster in this case, right? So that actually left a lot of junk because you see, in this case, do you see these text files here? So we did cat work 0.text. It'll show us like a number here. Cat work 0, let's say,
Yeah.
or 8. You see 904 here. So basically, our program took like we had all our children write to this text file with their values, and then they all communicated back to the parent saying that they're done. Then the parent goes through every single text file, extracting the number out of those text files, and then adding them up together.
Okay. Mm-hmm.
Yeah, so this is how you could process massive amounts of data in parallel fashion using C. This is one example. You could do threading too, but since we're doing fork exec, I thought it's a good example. So
I see. Mm-hmm.
so I mean, we could even go as far as like, for example, do 100 of these, right? So what happens if we do 100 of them? So sorry, I should have made these all constants.
Yeah, or yeah, like a variable name or something.
Yeah, let's just do 100 and see what happens. All right. So if I were to GCC main.c again, okay, and then let's check out vtop, right? If I did a.out, notice how that I have 100 processes now, and I get this right away.
Mm-hmm. That's pretty cool.
Yeah, I had 100 processes. So yeah, I wanted to see if we can actually get the CPU to update. So let's sleep for like I think for a brief moment it's gonna spike, but maybe not because I'm sleeping. So let's see. Yeah, it's fairly easy on the CPU. So yeah, that's about it really. So yeah, that's like a fork exec example. So these are system calls for your OS. Most of the time, like you want to just call fork to create a copy of the parent process. After you've done that, usually you want to do one or two things. You want to do some work, extra work that's only relevant to the child. Notice how with this pattern here, we're still using the same program, right? We didn't exec to write over the program. We used the exact same program. And it's just that we had a different path for children to take. That's all. That's the difference, right? Another example was to replace the entire program with some other program. So that was the exec example where we had to use exec. So okay, yeah, like most of the time you'll do a fork exec, right? But there are some times where you would want to actually just take a different code path for the child and do the work pertaining to the child there on the same program. And this is where, this is where checking for the child PID to be 0 works in this case. Or sorry, not works, where it's actually useful, right? Anyway, that's all I had for exec. So yeah,
Okay, sounds good. Thanks.
thanks.